do this later. Okay, you know where to go for the project. So this is on the CoCalc and the ISci Math under the AMO Journal Club.
Yeah.
Okay. And so I said we may need to pip install PyFFTW. Well, you don't need to, but it'll probably improve performance a little bit.
Running running terminal commands like that, I would just SSH in the CoCalc and they do all that. That's
yeah. Have you set up everything? So there's sort of a process that we have.
Is it by project or by account? I've done it for my account for the Forbes group one, but I don't know if I've
the SSH.
Yeah. Mm-hmm.
Have you also set the LC environment variables?
I think so. I'll have to double check though.
Okay, well, you'll see then. So I guess I should share the whole screen. Let me share the whole screen. Maybe I should try it again. Okay, so this is what happens when I log in. SMC, because I call it Sage Math Cloud. I started way before they changed their names. So if I'm here, if you look at your environment, I pass in the LC HG username, LC editor, and the Git stuff.
Okay.
And then this makes it so if you use version control, everything's set up. And then the .bash aliases file runs and sets things. Like, for example, it'll configure Git and everything. So that works.
Nice. Where do you have a script to set these up, or do you just define it in like your bash RC or something?
Well, this is bash aliases. It's on CoCalc.
Yeah. Okay. Gotcha.
And the way I do this actually is I install the MMF setup, and then MMF setup has a CoCalc option, which will set everything up for a CoCalc project. So it creates that bash aliases file and creates some links and stuff like that.
Gotcha.
And most of it's symlinked. So you can see here, like hgignore is symlinked to a place. Bash alias is a symlinked to this place. Right, so these symlinks are the files that my script installs.
Gotcha. Okay.
There's an HGRC file that does the that sets the username this way, enables some extensions, and gives you the HGLG command and stuff like that. No, this is not giving you the HGLG command. Why is that not giving you? Oh, maybe it includes it from the other one. Yeah, it includes it from the other one.
What does LG stand for?
It's like log, but it's a nice, pretty log.
Sure.
So if you go to repositories, here, I'll just do the MMF setup one. HGLG does this, which apparently is nothing. There we go. All right, so it prints a short version of the revision with a graph on the left-hand side, and I find it easier than any of the other things.
Yeah.
Okay, so we're in the AMO. So I might as well do it here. So Anaconda 2020. That's required on CoCalc. It's a CoCalc specific thing, but it activates the Anaconda environment. It probably does the equivalent of something like module load Anaconda or something. And then once that's done, you can create Conda environments, etc. Keep in mind that they take a lot of space and you don't have tons of disk space in the projects. So I'm using just the standard one for now. The problem with the standard one is you can't Conda install stuff because you don't have write permission, but you can pip install stuff. So we can go PyFFTW. Let's see if that works.
They still recommend running like Python -m pip.
Yeah, you should do that. Right. So the right thing should be Python-m pip. There. Thanks.
Yeah.
Okay, so that should be in there. Let's go back to the notebook now. I'll just share the whole screen. Can you see that okay if I do that?
Yep.
All right, fine. All right, let's see what happens if we restart this. And whoops, I don't like these messages popping up like that. It's kind of annoying. We should do something. Okay, it's not complaining. Don't know if it'll run, but we'll see. Okay, so this is the paper, the Quantum Lisa-G SCAR paper. They're putting just this, it's a 2D harmonic oscillator with some impurities. I don't know exactly what they do with impurities. You can read the paper and maybe do something a little bit better, but I've tried to do it, okay? Mm-hmm. There's probably some issues with the units. Here I'm taking these to be 1, but when I follow the supersymmetric method, I'm taking them to be these values. This is specifically to use this equation, which is implemented in the code down here for the wave function. You got to go through and make sure that everything's consistent.
All right, I'll check that.
I'll let you fix that up. Okay, this is correct. This is the energy eigenvalues, right? And then, so the point is, with different alphas, you can get degeneracies, and so you want to try and figure out where these are. Let me grab the paper.
And alpha is the ratio between, yeah, it's listed there, I see now. The ratio between the frequencies.
Correct. Is this the right one? No. There we go. Okay, and here's the Lisa Juskar paper. Probably should get the version, maybe the published version, because, yeah, I'll leave this here. Because this version has errors. Like they say this is the elliptic potential 1,2, but it's actually 2,3. They say it in the text here. Right? And this alpha is actually a pattern from 2,3. So I had some issues with that to begin with. All right. And then this is the wave function solution. It's in terms of Hermite polynomials, right? This is the exact solution for 2D harmonic oscillator. Of course, these things look useless because they're boxes. Right? It's Hermite polynomial on X, Hermite polynomial on Y. You know what I'm saying?
I think so.
Like if you look at one of those solutions, it looks like this.
Yeah.
That doesn't really look like a harmonic oscillator. I'll tell you how you get that in a second. Now, in order to compute these, you need to numerically either evaluate the Hermite polynomials, but those things don't scale very well. So it actually works out much better to do a recursion relation. So the ground state is the Gaussian normalized. This is normalized in these units, I think. Check that. And then this is the first excited state, and then there's a recursion relation for the wave functions. This will give you problems with cancellation at some point. There's a stack exchange answer, which relates to some code, which I think this is broken. I think there's a small error in this code, I can't remember, but I have an implementation somewhere, I just couldn't find it. You basically keep track of the magnitudes of the various terms and just make sure that you add them carefully. Right, so they remove the scale, then they add everything, and they put the scale back in. And then you can calculate these to hundreds or thousands orders stably.
What's the purpose of removing the re-adding scale?
So you don't get round off error, cancellation error from the terms, right? So these, I mean, the Hermite polynomials are really bad because you have an, exponential suppression, but exponential amplitude. And so if you compute the terms independently, if you do this, right, this will become exponentially large, not so far out. And then that gets killed by this Gaussian. But you can't actually compute the polynomials past a certain radius for large n.
Okay.
Right, so that's where that goes, right? So if you use this one, this is scaled a little bit better. This includes the Gaussian factor. But even here, you still get some issues where I can't remember. I think some of the terms go too small, but then they come back. And so you basically just keep track of the scale separately while you're doing the calculations and then put them back together. There's a paper here that you can look at.
That avoids the machine precision errors.
Yeah, and so this works quite nicely. Okay, so that's there. You can do it. We don't need it here. The recursion relationship that I implemented, which is just based on this, works well enough for like around 100, which is what we're using. So this chunk of code solves the problem exactly, basically. Okay, so I'm setting these are my units, setting my physical units. These are all 1 in the appropriate units. So that's what this is here. Right. So this is how, do you know about undimensionalization?
Yeah.
Yeah, okay, fine. So then this is my get psi. This is recursive, so it could be, exponentially complicated, so you should memoize. Do you know about memoization?
I do not.
Okay, so memoization is what you do is you make a dictionary and you store previous results in the dictionary. So that way you compute this for certain values of, you never repeat the calculation.
Okay, yeah, that makes sense. Okay.
And then it becomes tail recursive. Not tail recursive, but linear. Okay, and I do some checks to check that they're orthogonal and stuff like that. This is bad. You can implement this much better, but I just was in a hurry to get it done. So this computes the energies times h bar, or divided by h bar omega, for a bunch of n's and a bunch of y's for a given alpha. And then it just sorts them, and then it just returns all of the n's in order from lowest energy to highest energy.
What does the ravel do?
Makes it 1D.
Okay.
So this makes the nx goes down and y goes across. nx, this quantity here, this is a 2 by 2 matrix where nx is going down and y is going across. So this is all of the values. Do you understand?
Yeah.
And then Ravel turns it into a big long 1D array, and then you sort it, and then, right? So you can do this by counting, right? So nx will go out, whichever is smaller, omega x or omega y, that energy will go up, and then at some point the other energy will come up, and then that should go down when the other one goes up, and it should go right. You know what I'm saying?
Mhm.
So you could come up, I'm sure, with a much better, faster, simpler, not simpler, but much better and faster way of calculating this. But I did this brute force just to get it done. Now here I've obviously changed units, probably not a good thing, so check carefully. So here I'm getting those energies, but let's make sure this all runs. So bam, we'll do that. Here we'll get these guys. Okay. This is a, forget it, don't worry about that error. All right, so what I'm doing here is I'm doing a 10 by 5 grid. Now, you have to figure out how big to make this, and so the thing to do is to use Rx and Ry, which is the Thomas Fermi radius. Do you know what I mean by that?
I do not.
So for a simple harmonic oscillator, you have a kinetic energy and a potential energy. And so the furthest that the particle would go out classically is where the kinetic energy is there and the potential energy is E, right?
Yeah.
So this is E. This is the 245th, what 3,453rd state, right?
Mhm.
Ordered with that alpha. This is the energy of that. So here's the 2 times the energy over m. Well, here, let me write it out, right? So for the 1D harmonic oscillator, we want to find out what is the maximum extent. And so the maximum extent is where the energy is equal to m omega squared r squared over 2.
Yeah. Okay.
Right? And so the 2 goes over here, over the m, right? Square root divided by omega. That's what this is.
Gotcha.
Got it? Okay, I'll let you document that if you think it should be documented. So I'm choosing that as my limits. Interesting. I thought I made it slightly larger than that. I'm not quite sure why this box isn't tight with the cloud, but maybe that's because of the 2D or something. Oh, yes. Okay. I probably somehow neglected something with 2D or with, anyway, so it works well, but it works better than I expected. So then I'm just making a figure and with the right size. This is the mesh, okay, for the X and Y coordinates. So let me just go through this loop. So I'm just randomly, these are just random states. So what I'm randomly doing here, I'm getting all of the states where the energies are close by. So for, if you choose commensurate frequencies, like I've done, like alpha is 2/3, these would be all the degenerate states with that same energy. You could put a different relative tolerance here, and that would get many more states. But it's getting a bunch of states within a certain region. You can play with that. Make sense?
Mhm.
And let's just print this. So you see, so for this particular state, you know, there's one, how you count. But those states all have the same energy. Okay? All right. So now what I'm doing is I am randomly generating amplitudes and phases. Okay, so I'm generating, what is this? 1, 2, 3, 4, 5, 6, 7. Let's say this is 20. I don't know what it is precisely, okay? But I'm randomly generating 20 phases and amplitudes. The amplitudes go from 0 to 1. And the phases are just arbitrary phases, 2 pi times j times random numbers from 0 to 1. Make sense?
Yeah.
Okay, and then what I'm doing is
I'm
I'm taking my wave function to be a sum of the eigenstates. So
Right.
these should be the eigenstates. I'm using my get psi function above. I had to make it dimensionless. I probably need a dimensional factor over here, but it doesn't matter because, you know, this is just a wave function. and I'm adding them up together. So these are random combinations of the eigenstates. If you take one of them, it looks like this, but if you take random combinations, then you get the harmonic oscillator structure. And I'm just doing this with different seeds. So I'm creating
Oh, okay.
50 different random realizations. And then if you look at this, you'll notice that some of these have quantum scars or things that look like scars, right? So there's dark regions that correspond presumably to some sort of trajectories that are classically stable, or maybe not stable, but solutions to the classical equation of motion. This doesn't look particularly good. What if we try another seed? Yeah, so for example, here you're seeing something that's reminiscent of the alpha Lissajous figure, right? Anyway, so okay, so that's sort of where those are coming from. Make sense? And these are analytic, so we're definitely set there. I'll just make sure this actually plots, but okay, fine. So this is just one of the states. Now, I want to be able to solve this with perturbations, so I have to try and figure out how to solve it. Did you think about that problem at all?
I have not, no.
Okay. So the basic idea is you can get the ground state if you evolve the Hamiltonian under imaginary time, right? So if you expand this in terms of the energy eigenstates, it'll be, whatever state you start with will have it'll be a sum of coefficients times the energy eigenstates. And then this exponential factor will decrease faster for high state energies and slower for low energy states.
Okay, gotcha.
And so if you take t goes to infinity, only the component with the lowest energy will survive. Now you have to make sure your initial state overlaps with the ground state, but if you do, then you'll get the ground state. You have to renormalize, because of course everything will go to zero if the energy is a positive, which they are. So that's how you get the ground state. Now we want to get not the ground state, but we want to get an excited state. And there are various algorithms for getting an excited state. And I have not had the patience to really play with them, but you should maybe look at that. But what you can do here is you could do something like this. So if you take the Hamiltonian, now I don't know, I've actually just made this up myself. I don't know if this is a good procedure or not, but it kind of works, so I'm doing it. So what I'm doing is I'm taking the Hamiltonian, I'm subtracting off the energy that I want, and I'm squaring it.
Okay, so as long as it's the energy of whatever state is close to that energy that you choose,
that'll be the new ground state.
Right.
It's probably a bad idea in the sense that
why do you have the square there?
Pardon?
Oh, okay, for absolute value. I see. Okay.
If you don't square it, all you're doing is shifting the Hamiltonian, and this will still give you the ground state. It's just now the ground state has you've tried, right?
Right.
Now, the way that this is done in the literature is something called the shift and invert. So basically what you want to do is you want to shift the Hamiltonian by your approximate energy, but then you invert it so that it blows up at that point. And that will, if you happen to be actually at the eigenstate, that inversion procedure will give you the eigenvalue. I'm not sure if you're, sorry, eigenvector. I'm not sure if you're aware of this.
No.
Right, so once you get, so the way you solve eigenvalues and eigenvectors, the way you solve the eigenvalue problem is some sort of form of the determinant. You don't actually do that, but you basically try and find what the eigenvalues are. And once you have an eigenvalue, then what you do is you invert this matrix, right? And you're looking for the state that where h times that state is equal to e times that state, right? So that would be a null state of that matrix, of this shifted matrix. And so basically, if you use one of the solver routines, like a LU decomposition or something to do that, of course, it's a singular problem, but you'll find that state very accurately. So that's how you actually go about constructing the eigenstates, the eigenvectors from an eigenvalue. And so the shift and invert procedure uses that, except takes an approximation for the energy and then works through to calculate the eigenvectors that way. However, it was running really slowly, so I got bored and you can't get feedback while it's running, so I gave up. So I just am doing this because I do this all the time. But because this is quadratic and not linear, it probably doesn't converge very well once you get close to the ground state, right? Like all the energies of the ground state are all smoothed out like this, right? Because you're taking your spectrum, you're taking the middle and you're squaring it. So it's no longer like anyway. So it's probably a very poor problem, but it gets you an idea of what's going on. We can discuss in Journal Club if we want to do something better.
Sure.
But that's what I'm doing. Make sense?
Yeah.
Okay. So here I'm doing the same thing as before, just getting my alphas, getting my n maxes, et cetera, my oscillator lengths. Now, these are the numbers you have to play with. So you need to play with the number of points, which should be an integer, and for performance reasons, it should be close to a multiple of 2 or 3. And then this is the size of the box, which I made it slightly larger than the Thomas Fermi radius. Again, you'll have to play with that, and I'll show you how in a second. Okay. Once you know those, you get the x and y coordinates, which is a range times dx minus L over 2. And do you know what this guy does?
I know what a mesh is, but
so this is just this is an array. Like these are all the x values.
Sure.
And then all the y values. So this list here is first the 1D array of x's and then the 1D array of y's. Do you see that?
Yeah.
Okay. And then this passes those one at a time to MeshGrid. MeshGrid takes a variable number of arguments. So I'm passing, it says like MeshGrid x comma y. And what that does is it takes those 1D arrays and turns them into 2D arrays with x going down and y going across.
Okay. Gotcha.
And then that's indexing ij means x goes down, y goes across. Otherwise, it swaps them from plotting, but it's kind of useless for numerical work. And sparse means that x goes down, but it doesn't fill out. So it's somewhat memory efficient. And then when you add x and y, it'll broadcast to get a full mesh. Make sense?
Yeah. Yeah.
Okay. Same thing for the momenta. These are the momenta that are required. So I'm using Fourier frequencies, n of them with this lattice spacing. You need to put the 2 pi in there because we work with angular units. Same thing. So the potential is just m omega x squared plus omega y squared over 2. And then I'm going to put the perturbation in. Right now, I'm doing the perturbation as a sum of Gaussians at random locations with a small amplitude.
What's the VP here? Sorry, I'm on
VP.
Yeah.
This will be the perturbation. So I'm just accumulating them all in VP.
Okay.
So I'm just using VP as the accumulator. Start out with 0. Yeah, probably should put it down here.
And what is Vx here?
Vx is the potential evaluated on the XY grid.
Okay, yeah.
Make sense? So this is harmonic oscillator, and then I'm adding random perturbations. And this is what the random perturbations look like. They each have a width of 1. They have an amplitude of 1/10 of the original potential. And they have random locations in the box. You'll have to look at the paper to see what they do. I can't remember how big the amplitude is or how many they have, etc. Okay, and I'm seeding the random number generator. So if you change the seed, you'll get a different pattern of things. You understand about that?
Yeah.
Yeah, okay, fine. But I always seed because you don't want to, you want to have reproducible results.
Yeah, that makes sense.
Okay, so then in momentum space, the kinetic energy is h bar squared over 2m times kx squared plus ky squared. So to apply the Hamiltonian, what do? Well, you take psi, you multiply by v, and then you take the Fourier transform of psi, you multiply by k, and you take the inverse Fourier transform.
Okay, yeah.
And then this is a sparse linear operator that does that. And this you could, in principle, pass to the sparse eigenvalue problem. And maybe you want to play with that and see if it actually converges or how long it takes. Maybe you lower the tolerance or something. Hello?
Yeah.
Oh, I see. Hang on. Khalid's talking to me on Mumble. Just give me 1 sec. Hi, I'm in a meeting with Will. Can you hear me, Khalid? You can't hear me. Khalid might pop in, but anyway, we'll keep going on here.
Sure.
Okay. So you can probably apply this. Now, here's what I'm changing. So this is the important thing. So what I'm doing here, again, check this because units, but I'm trying to get psi x and psi y for the maximum n, right? So if it was a pure oscillator in the x direction or pure in the y direction, make sense?
Mhm.
Then I'd get these, and I'm plotting them on a log-log scale, the absolute value of the wave function divided by the max. That's the left plot. And then the same thing on the right plot, but in momentum space. Make sense?
Yeah.
Okay. And what you want to see here, you want to make sure your box is big enough that these guys fall off to something like 10 to the minus 17 machine precision or so. So this box looks like it's too large. And the same thing here, you want to make sure that in momentum space, and this is how many points you have, it falls off to machine precision. That, if you do that, you can do it fairly tightly. That should guarantee that your process will converge. Does that make sense?
Mhm.
Okay. So to do that, you play with these parameters here. So if I divided by 4, you probably will see that the x position won't work so well. Right, so you see the x values, they're the solid. You have to know the colors of solid. I didn't put legend, but the x values, you see they're not falling off yet. So I don't have enough k, large enough k in x space to have those fall off.
Okay. And what happens if the box is too big?
You waste time.
Okay, that's what I thought. Just making sure there wasn't
So
some.
I just played with these by hand. You can actually calculate some of these, but there we go. Okay, so that's that. Once you have this and you're comfortable that you probably are doing the thing, I'm going to try and minimize. Now, I'm not doing the imaginary time evolution. What I'm using is I'm using the SciPy minimize function. And I'm minimizing this function. And so the derivative is given by this guy. You should verify this yourself. Okay. The wave function is real because the matrix is symmetric. This, of course, won't.
What is M here?
Pardon?
What is M?
M is the, M is probably h squared minus EH.
Okay.
Minus 2EH. But let's see, I have to figure it out. What do? I apply H and then I apply H again. Yeah. So M is equal to H squared minus 2EH. So it's not exactly the, so it's equal to, right, this is equal to H minus E1 squared minus E squared.
Yeah.
So I just remove this constant. Okay.
Okay.
So here's my function that applies it. This will fail at some point, but I checked it, so it works. But you should write a test for this, but we'll do that later. This is computing f and df, and I'm again using a cache, just briefly, because the minimizer, you have to pass both an f function and a df function, and it'll call them one after another. So I don't want to recompute this every time.
Yeah.
So okay, so I'm using a cache, but basically what I'm doing, S is this guy without a metric, sum of x squared. X is the full state psi raveled to be a long thing, and I'm using only real states because I'm just looking for eigenstates. I wonder if that's bad. Can we restrict the eigenstates to be real? In 1D you can for sure. In 2D I don't know. What do you think?
My intuition's yes, but I don't have a very good 2D intuition for this.
I mean, what about like so I mean, you can definitely have states in 2D that are eigenstates that are not. Like, you can have the p waves, the p states for hydrogen. The question is, can you always break them down into states that are real? Check that out, or give an argument that you can. This assumes you can. If you can't, then you have to expand. So here's what I'm doing. X is a 1D array. I'm reshaping it into the psi. I'm applying the Hamiltonian, and then I'm taking the real part and raveling it back.
Okay.
So that's M acting on X. So it's assuming X is real and it's treating it as a 1D real array only. Okay. Then F is M is the top part divided by S. DF is the right hand side here. Okay.
All right.
But what we would have to do is we would have to, like, the code would look like, you would want to go like this. Yeah, you'd probably go nx ny times 2 dot view d type equals complex, right? So take that real array, put it into an nx by 2 ny array, and then review it as a complex array, which would take the double extra components and put them all into real, imaginary, real, imaginary.
Yeah, yeah.
This is a little slick, so I'd probably want to call this, I'd probably want to add a new function called unpack and pack, which is what I usually do. But I thought this was clear enough if it's real. And again, then here we wouldn't be able to take the real part. We'd have to convert it to real so that the real and imaginary parts are appropriately staggered and then ravel it. Okay?
Yeah.
Here I'm checking the derivative just to make, so I'm numerically computing a finite derivative. And I'm checking that that agrees with the computation of df. And these numbers should be the same.
Yeah, okay.
To some precision. And so they are. So I think I've done it right. The reason I needed to do this scaling is otherwise, now there is a slight problem here. One of the slight problems is a singular direction, right? If you scale x, then f doesn't change because I'm removing that scaling.
Yeah.
I have a way of fixing that if you run into problems, but it's more complicated, so I didn't put it in. And this seems to work. All right, now I need to get an initial state. So, well, let me first stop. Okay, so I'm running the SciPy minimizer function, okay? This is using this limited memory BFGS minimizer. You should look that up. It's a nice minimizer using gradient directions, using Broyden's method to build up the Hessian, the second derivative matrix, but using a rank reduced version of that so that it does not take up too much memory. You can specify how many states you can use, and there's some parameters here that you might want to increase. Of course, you should look at your memory usage here and make sure you don't get too big. And I'm giving a callback, which every 100th step plots the state. This is the log of the state, and this is the state. And I started from a random initial configuration. Make sense? And this is the energy of this Hamiltonian, which is right, like it's the energy. What are we minimizing? We're minimizing H minus En, where En is actually the exact eigenstate without the perturbation.
Yeah.
Right. So it's like the energy difference between the two, maybe with a factor of 2. I might be wrong with that. But anyway, so this should be pretty close to 0 by the time it's done. Okay.
All right.
And so that's going ahead. And then this will minimize. And this is a pretty high tolerance, so this will take some time, but you could do it to a low tolerance first, for example, and then polish it to a higher tolerance after, if you wanted.
This is all to find the largest eigenstate?
This is to find an eigenstate with a large energy.
Okay, yeah.
And again, I don't know how well this is going to converge, etc. Now you could try and use, and I don't know how well it's going to work, but you can try and use sparse linear algebra eigsh. And this should find the eigenstate closest to this. I didn't have the patience to let this run. Okay, or maybe it actually failed, right? The inversion of this failed. So I gave up. In principle, this should work as well. Okay. I also tried making the entire matrix, but it's very big. And then you can find use a dense eigenvalue routines to get the answer. But that didn't work so well. Okay.
Yeah.
So these are the things you need to start exploring and understanding. Now, this doesn't show a quantum scar, but I read the paper a little bit more carefully, and they say, but in order to see those quantum scars, you basically need to start with something that's close to a class, like with a Gaussian wave packet that's close to a classical trajectory. Okay?
Okay.
You might be lucky and you might stumble on a state that has a quantum star. But to do that, what I did is I did this here, is I added to the random initial state that I was giving it before, I added a Gaussian at plus or minus these points. So I randomly picked a point on Y, which was halfway up.
Mhm.
And then I picked the point on X that corresponds to the same energy.
Gotcha.
And I put a Gaussian there and at the -1. So now you see if I run this, you'll see I have these two blobs here and here. And then you'll see that the minimization, as it runs, it starts to find, it'll move these blobs around and it finds this quantum scar.
Gotcha.
Now, I'm not exactly finding eigenstates here, right? I'm minimizing. And so the minimization depends on your initial state. Now, ultimately, if it converges to the lowest eigenstate closest, there is only one, right? Because this is a discrete system and everything should be discrete.
Mhm.
And so if you run this far enough with a high enough tolerance, you may get there, but you might not be able to get there because this is a minimization routine. And as I said, the energy is quadratic, it's flat.
Right.
It might even be quartic because I've done my stupid square thing. And so, you'll get the energy to very high precision, but you won't get the state to very high precision. And this is always a problem with minimization. And so using an eigenvalue solver would be a much better thing to do. But as I say, I couldn't quite get it working. And I don't know if this is one of the things we should discuss in the paper. I don't know if the paper is correct. Like when they say that that is an eigenstate, you know what I'm talking about? When they say, where is it? It's over here, right? When they say this is an eigenstate, I don't know that I believe this. If they're using imaginary time evolution, I'm not sure that they're necessarily getting an eigenstate. Maybe they are, right? They're using imaginary time evolution on the original Hamiltonian orthogonalization as they go. That's what this ITS algorithm, the ITP algorithm does. But I don't know. Right, so they say here that coherent states, okay, here we want to emphasize the fact that quantum solutions presented in 2, the exact ones, have rectangular symmetry, even in the limit of large quantum numbers. Hence, the eigenstates of 2 do not show any features of classical POs. In order to describe them, one can construct a coherent state for a 1D oscillator, right? So basically a wave packet, whose center follows the corresponding classical trajectory, right? So the Schrodinger coherent state must have a wave packet with its center mimicking the classical trajectory. So you do this, but then, like what I don't know is, I don't know if you look at the actual exact eigenstates for the system with their perturbations, is there guaranteed to be one that always has a scar? Or several that have scars? Or does that depend on the perturbations? I mean, so obviously if you randomly take the degenerate states and you merge them together, if you do it in the right way, you get scars, right? But it's not clear to me that randomly putting Gaussian bumps, which will split those degeneracies, will give you states that have scars. Now, the density of states is large, so there's definitely states that are close to states that have scars, but maybe they're a mixture of 2. I don't know. Do you see what I'm saying?
Yeah, I do. Sorry.
Okay. So here I'm starting out with a state. So what they recommend is that you should actually start out with a state that has a density in the classical trajectory, right? So I didn't do that. Oh, this bailed out too early. So let's do it faster. But what you find is that even if you start at these points, this will actually, I mean, it looks like this down here, right? So it'll actually produce this scar-like state. I doubt this is an eigenstate, but it's close to an eigenstate. And so it's, right? You know what I'm saying? Because we're minimizing, so we're getting closer. But I don't know if any of the exact eigenstates actually have these scars or not. This is one of the questions I want to ask and talk to Steve. And maybe you can figure this out. Maybe you can actually run the minimizer and get something. Or maybe you want to work with slightly smaller systems and see if there's scars there. Or, okay, at this point, you basically take off and start playing and exploring. But is it clear what I've done?
Yeah.
Okay, let me see if there's anything else in here. So, oh, yeah, so this is just for discussion, but so if you take, for example, a Gaussian wave packet expands like this, there's actually a nice article on Wikipedia that gives you all the details. I wanted to figure out how fast it would expand. So I'm kind of wondering if you have a small particle and you start with it, not a really small size, but a fairly small size, like maybe 1,000th, like a millimeter or something. It would take on the order of 10 to the 23 years before it expands. And so that particle would bounce around in a stadium, I think. And if you had two of those particles and you give them small perturbations in their initial condition, they would look chaotic to me until times that are long. So I want to ask Steve about some of these questions, but that's all I was doing here. And then I was looking in 1D at some evolutions of wave packets in a potential with a Gaussian bump. So, but can they actually fall off? But I don't know if that's relevant or not. So, and my question is, if you did the stadium thing with like infinite but walls, when the particle bounces in, how does a Gaussian bounce off? This may be something you want to do. How does a Gaussian wave packet bounce off a hard wall? Does that cause it to expand more rapidly or not? I don't know. Do you know?
It's been a minute since I've looked at reflections and such.
So it might be that every time you hit the wall, it actually causes the thing to expand faster. So this Tmax might be a bad estimate when there's multiple collisions. So that would be something to ask here. And presumably that depends on how fast it hits the walls. So, right. So I'd like to get a good estimate of how long the system will remain classical, like with coherent states bouncing around.
Gotcha. I've arranged to meet with Kartik right after this, so I can.
Okay.
I'll bring this up with him.
Fine. Anyway, that's it. I think that's all I have now. You can see this is running on CoCalc. It's a little slow here, but you can sort of run it later. Wonder if let me just try one other thing. Let me try running it with the BFGS method. This is not limited memory, but in principle can do a much better job. You see the memory usage is going up. Yeah, no, we ran out of memory. Okay, it makes a full set of states, but for this big problem, that just takes too much memory. So you're stuck with using this guy, but you can increase the number of states. What's it called? It's called, yeah, this is it here. See how you pass these things in through the options and max core. Yeah, we could probably bump this up quite a bit and it might do a much better job. So let's try that. Let's try options equals dict max core. Was that the way it was spelled? Yeah, okay. Let's try 100. Maybe even 1,000. We can probably get away with 1,000. All right. I don't know how much of this I have to run again, so I'm going to run it all.
I tried to skim it while you had it up, but what is max core changing? It's like something with corrections.
Oh, so what this is doing, if you want to do a minimization, you have to have a Hessian, right?
Mm-hmm.
Like you've got the gradient descent, and so you're going to go downhill, but you want to get to the minimum, so you actually want to have a quadratic approximation of that. And then you could do Newton's method on for the root finding problem of finding where the derivative goes to 0. Does that make sense?
Yeah, yeah.
Okay, so that's what you're trying to build up the Hessian, but the Hessian, of course, takes n squared elements. So if your matrix is n by n, then this would be n squared by n squared, which is really big. Yeah. So what this does is it uses a rank deficient, like a reduced rank approximation of the Hessian using what's called Broyden's method. That's the B in the algorithm.
Okay.
I did something wrong here. What did I do wrong? Why does that not work? Okay, there we go. And so this is the number of components in that rank reduced operation that they use.
Gotcha.
It has a funny term, but that's basically it. So the BFGS algorithm uses max core is basically the number is n squared. So it's the full matrix. But that of course can be very inefficient memory-wise. And we just ran out of memory. So this will gradually build up 1,000 of these guys. Making this too large might actually slow it down. It'll make it take less steps to converge, but it might actually slow down each step. So I don't know what the optimal value is. In the code, they recommend 10, right? I mean, they're using 10 as the median, as the regular value. So you'll have to play with that a little bit. Make sense?
Yeah.
All right, I think that's it then. I'll stop the recording
All right.
and I'll send you that.